Imagine being teleported to a time when stepping outside meant facing predators with 6-inch serrated fangs, where the average temperature could kill you in hours, and where 70% of land was either scorching desert or toxic wasteland. Now imagine that diving into prehistoric waters filled with sharks was actually your safest option. This wasn't a nightmare or an alien planet. This was Earth during the Lopingian Epoch, the only time in our planet's 4.5 billion year history when aquatic environments offered better survival odds than dry land. For 7 million years, between 259 and 252 million years ago, our world transformed into such a hostile realm that even hardened paleontologists struggle to comprehend how anything survived at all.
The numbers alone paint a picture of an alien Earth. Days lasted only 22 hours instead of 24, meaning each year contained 400 days rather than 365. The moon orbited 15% closer to Earth, appearing nearly twice as large in the sky and creating tides 40% stronger than today's. Global temperatures averaged 35 degrees Celsius. That's 95 degrees Fahrenheit, making the entire planet feel like Death Valley in summer. But these statistics merely scratch the surface of the Lopingians' terrifying reality.
Geography itself had become unrecognizable. A massive supercontinent called Pangaea contained 92% of Earth's land surface, creating a solid mass larger than all current continents combined. This geological monster stretched 13,000 kilometers from north to south and 11,000 kilometers at its widest point. The remaining 8% of land existed as isolated islands, with the largest combining present-day Siberia, Kazakhstan, and northern China into a landmass roughly 4 million square kilometers in size. Surrounding these lands, the ocean statistics boggle the mind. Pangaea, the superocean, covered 68% of Earth's surface, containing 1.2 billion cubic kilometers of water. For perspective, that's 40% more water than all modern oceans combined. The Tethys Ocean added another 12% of planetary coverage, while the Paleotethys contributed 8% more. These vast water bodies maintained average temperatures between 28 and 32 degrees Celsius, creating planet-wide tropical conditions.
But here's where the story takes its strangest turn. Despite their intimidating size, these oceans were surprisingly empty of large predators. The marine fossil record reveals a shocking statistic. Large predator diversity had crashed by 78% compared to earlier periods. The biggest sharks, the eugenodontids, averaged only 2 meters in length, with maximum sizes reaching just 2.5 meters. Compare this to earlier periods when marine predators regularly exceeded 8 meters and the oceans suddenly seem almost peaceful. The extinction statistics explain this emptiness. The Capitanian mass extinction event, occurring just 2 million years before the Lopingian, had eliminated 67% of marine families and 82% of marine genera. For comparison, the asteroid that killed the dinosaurs only eliminated 43% of marine families. The oceans hadn't recovered. They were essentially biological deserts with scattered oases of life.
Shark populations tell this story clearly. Where once dozens of species patrolled every ocean zone, Lopingian seas contained only 12 known shark species across 3 families. The xenocanthids, freshwater sharks that had thrived for millions of years, were reduced to 3 species. The Hybodontiformates, despite being the most successful group, numbered only 7 species. The Ctenocanthes barely survived with 2 known species. Maximum shark density in even the richest waters rarely exceeded 1 individual per 10 cubic kilometers. Even more telling were the Eurypterids, the sea scorpions. These arthropods had once reached 2.5 meters in length and dominated marine ecosystems. By the Lopingian, only 2 genera remained, neither exceeding 50 centimeters in length. Their population density had crashed by an estimated 95%, leaving vast stretches of seafloor essentially empty of large arthropods.
The statistics for other marine groups paint an equally grim picture. Trilobites, after 270 million years of success, were down to their last 4 families from a peak of 82. Ammonoid diversity had plummeted by 73%. Brachiopod species numbers dropped by 67%. Crinoid populations crashed by 81%. The oceans weren't exactly safe. They were simply less dangerous than the hellscape above water. On land, the statistics tell a completely different story, one of predator abundance that defies modern understanding. Fossil sites from the Lopingian reveal predator-to-prey ratios that shouldn't exist. In the Karoo Basin of South Africa, fossils comprise 35% of all specimens found. Russian sites show even more extreme numbers, with some formations containing 42% predator remains. For context, modern African savannas show predator fossil percentages below 5%.
The Gorgonopsids led this predatory explosion. Starting from humble origins as 30-centimeter-long hunters, they underwent one of the most dramatic size increases in evolutionary history. By the Lopingian, the largest species had grown by 1,200%. In Austransavia, the apex Gorgonopsid reached lengths of 3.5 meters and weights exceeding 450 kilograms. But size statistics only tell part of the story. Their dental weaponry achieved terrifying proportions. Upper canines in large Gorgonopsids averaged 12 centimeters in length, with record specimens reaching 15 centimeters. These weren't simple fangs. Microscopic analysis reveals serration densities of 8 to 12 serrations per centimeter, each perfectly angled for maximum cutting efficiency. The teeth carved backward at a 15-degree angle, preventing prey from pulling free. Tooth replacement rates averaged 1 new canine every 8 months, ensuring these weapons stayed sharp.
Geographic distribution data reveals the true extent of Gorgonopsid dominance. Fossil evidence places them across 14 million square kilometers of Pangaea, roughly 40% of the supercontinent's habitable land. Individual species like Innistransvia occupied ranges spanning 6 million square kilometers, adapting to environments with temperature variations exceeding 50 degrees Celsius between regions. Population density estimates based on fossil accumulations suggest mind-boggling numbers. In prime habitats, large Gorgonopsids may have reached densities of 1 individual per 2 square kilometers. For 400-kilogram apex predators, this density exceeds anything seen in modern ecosystems by a factor of 10. The herbivore populations necessary to sustain such predator numbers must have been extraordinary.
The rubigenids of South Africa present even more extreme statistics. This Gorgonopsid subfamily included 9 genera, with 6 exceeding 2.5 meters in length. In some fossil sites, rubigenid remains outnumber all other predators combined by a ratio of 3 to 1. Their skull proportions were remarkable, making up 18 to 22% of total body length, compared to 12 to 15% in modern predators. Bite force calculations reveal surprising data. Despite their massive skulls, Gorgonopsids generated relatively weak bites, averaging 650 to 750 newtons for the largest species. Modern wolves produce 400 newtons, while lions generate 1,000 newtons. This weak bite actually demonstrates remarkable efficiency. With teeth designed like surgical instruments, they needed minimal force to inflict catastrophic damage.
The Therocephalians added another statistical layer to Lopingian predation. With 34 known genera spread across 6 families, they achieved greater diversity than Gorgonopsids, despite generally smaller sizes. Size distribution data shows interesting patterns. 45% of species remained under 1 meter, 35% ranged from 1 to 2 meters, 15% reached 2 to 3 meters, and only 5% exceeded 3 meters. Venom evolution in Therocephalians represents a major innovation. Skull analysis of Euchambersia reveals grooves consistent with venom delivery in 4 separate specimens. If confirmed, this pushes back vertebrate venom evolution by 20 million years. Dosage calculations based on gland size suggest enough venom production to kill prey items up to 200 kilograms, well within the size range of contemporary herbivores.
The reptilian predators add more sobering statistics. Archosauromorphs, though not yet dominant, included 15 known Lopingian genera. The Proterosuchids alone comprised 8 species, ranging from 1.5 to 4 meters in length. These crocodile-like predators achieved population densities of approximately 1 per 5 square kilometers near water sources. Freshwater environments hosted their own statistical nightmares. Temnospondyle amphibians reached unprecedented sizes during the Lopingian. Prionosuchus measured up to 9 meters long, larger than any modern crocodile. The rhinosuchids included 12 species exceeding 2 meters, with 3 surpassing 4 meters. In suitable habitats, large temnospondyle density reached 1 individual per 500 meters of shoreline. Herbivore adaptations reveal the intensity of predation pressure through measurable changes. Burrow dwelling became so common that 40% of known Lopingian herbivore species show adaptations for digging. Lystrosaurus burrows average 1.8 meters in depth, with some reaching 2.5 meters. Tunnel systems could extend 15 meters horizontally, creating underground networks covering 200 square meters.
Armor evolution reached extremes. Scutosaurus possessed over 200 individual armor scutes, each averaging 5 centimeters in diameter and 1.5 centimeters in thickness. Total armor weight comprised 18% of body mass, equivalent to a human wearing 15 kilograms of protective gear. Bone density measurements show values 40% higher than modern reptiles, approaching the density of stone. Size increases in herbivores followed predictable patterns. Average herbivore body mass increased by 340% between the early and late Lopingian. The largest periasaurs reached 1,500 kilograms, while earlier relatives rarely exceeded 400 kilograms. This size increase directly correlates with predator size evolution, maintaining a consistent 3-to-1 prey-to-predator mass ratio. Climate data from the Lopingian reveals wildlife concentrated in specific regions. Global average temperatures of 35 degrees Celsius masked extreme regional variations. Equatorial regions regularly exceeded 45 degrees Celsius, with ground temperatures reaching 60. These zones comprised 35% of Pangaea's surface, creating vast dead zones where even extremophile bacteria struggled. Rainfall patterns created additional challenges. The supercontinent's interior received less than 100 millimeters of annual precipitation across 40% of its area. Coastal regions experienced monsoons delivering 2,000 millimeters annually, but these areas comprised only 15% of total land. The remaining 45% experienced irregular rainfall between 200 and 800 millimeters, creating unpredictable conditions. Atmospheric composition differed dramatically from today's values. Oxygen levels averaged 16% globally, but dropped to 12% at sea level in equatorial regions. Carbon dioxide concentrations reached 2,000 parts per million, 5 times pre-industrial levels. Methane levels spiked to 1,800 parts per billion, contributing additional greenhouse warming. The day-night temperature variations reached extremes unknown today. Continental interiors experienced daily temperature swings of 40 degrees Celsius. Desert regions could reach 55 degrees during the day and drop to 15 degrees at night. These 40-degree variations occurred over just 11 hours of daylight and 11 hours of darkness, creating rapid thermal stress.
Wind patterns achieved destructive intensities. The temperature differential between Panthalassa and Pangaea's interior generated winds averaging 120 kilometers per hour, with storms reaching 200 kilometers per hour. Dust storms could last 20 days, carrying particles across 5,000 kilometers.
Some regions experienced 100 major dust events annually. UV radiation levels present alarming statistics, even before the end Permian ozone depletion. Thinner atmosphere and higher solar angles produced UV indexes averaging 15 at midday, far into the extreme category. Some equatorial regions reach UV index values of 20, capable of causing severe burns in minutes. The transition to the end Permian extinction shows through changing statistics. Volcanic activity from the Siberian traps began 251.9 million years ago, initially producing 1,000 cubic kilometers of lava annually. This rate increased to 4,000 cubic kilometers per year at peak activity. Total lava volume reached 4 million cubic kilometers, enough to cover all of modern Europe 400 meters deep. Gas emissions achieved catastrophic levels. Carbon dioxide releases totaled 30,000 gigatons over 600,000 years. Sulfur dioxide emissions reached 6,000 gigatons, producing acid rain with pH values of 2.8, more acidic than lemon juice. Methane releases from clathrate decomposition added 5,000 gigatons more carbon to the atmosphere. Temperature spikes during the extinction reached incredible extremes. Global averages jumped from 35 to 45 degrees Celsius in just 20,000 years. Some regions experienced increases of 15 degrees in under 1,000 years. Ocean surface temperatures reached 40 degrees Celsius at the equator and 32 degrees at the poles. Uniformly lethal conditions. Oxygen depletion accelerated dramatically. Atmospheric oxygen crashed from 16% to 10% in 60,000 years. Ocean oxygen levels dropped by 80%, creating dead zones across 70% of marine environments. On land, the combination of heat and low oxygen reduced survivable habitat by 85%. The extinction statistics remain sobering 252 million years later. Marine species loss reached 96%, the highest of any mass extinction. Terrestrial vertebrate species loss hit 70%. Insect species, normally extinction resistant, suffered 65% losses. Plant species extinction reached 60%, fundamentally altering terrestrial ecosystems. Recovery timescales exceeded all other mass extinctions. Full marine diversity recovery required 10 million years. Terrestrial ecosystem complexity took 15 million years to restore. Some groups never recovered. Gorgonopsids left no descendants despite their Lopingian dominance. Others, like therapsids, survived but took 30 million years to regain prominence. The Lopingian statistical legacy extends beyond extinction numbers. This period demonstrated that predator-dominated ecosystems could exist, challenging ecological theories about sustainable population pyramids. It proved that global temperatures could exceed levels considered lethal to complex life. Most remarkably, it showed that aquatic environments could become refugia when terrestrial conditions grew too extreme.
Modern climate parallels provide sobering context. Current CO2 levels of 420 parts per million seem modest compared to Lopingian values of 2,000, but the rate of increase mirrors end Permian patterns. Today's temperature rise of 1.2 degrees over 150 years seems gradual, but it matches the initial stages of past catastrophes. Ocean acidification currently proceeds at rates comparable to extinction intervals. The Lopingian epoch stands as Earth's greatest natural experiment in extremes. For 7 million years, our planet tested the absolute limits of what complex life could endure. The statistics tell a story of a world so hostile that even evolution's most fearsome creations struggled to survive. When diving into shark-filled waters becomes the safe option, you know you've entered one of history's strangest chapters. This ancient period reminds us that Earth's hospitality toward life exists within surprisingly narrow parameters. The difference between a thriving biosphere and the nearly dead planet can be measured in just a few degrees, a few percentage points of atmospheric composition, or a few million years of volcanic activity.
The Lopingian world, where 22-hour days saw temperatures that could kill, where predators outnumbered prey, and where water offered better odds than land, seems impossibly alien. Yet it was very much our Earth, following the same physical laws and biological principles we see today.
Understanding the Lopingian means understanding that our planet's capacity for extremes far exceeds human experience. It means recognizing that the stable, life-supporting conditions we've enjoyed throughout human history represent a vanishingly small fraction of Earth's possible states. Most importantly, it demonstrates that once environmental systems begin cascading toward extremes, the results can persist for millions of years and reshape life's entire trajectory. The ultimate lesson from Earth's strangest period isn't just about prehistoric monsters or alien-seeming worlds. It's about recognizing that our planet's biological and climatic systems can enter states so extreme that even imagining survival becomes difficult. In an age of rapid environmental change, the Lopingian stands as both a fascinating glimpse into deep time and a stark reminder of just how far conditions can deteriorate when critical thresholds are crossed. The fact that water once offered better survival odds than land isn't just a curious historical footnote. It's proof that on Earth, the unthinkable can become reality.